Alright, so in this video I'm going to go through one of the specimen papers for AQA A-Level Physics. This is for a paper 2, and this is the second set of specimen papers, so it's not the one that's available on the website, it's another one that's also available. So, first question wants us to explain what is meant by capacitance. Well, capacitance is the charge stored per unit of potential difference across it. So 120 microfarads means you can store 120 microcoulombs per volt of potential difference across the plates. All right, so that's what we've got there. So what we've got here is some apparatus used to measure the speed of a steel ball immediately after it's been struck from rest. So this is very similar to a previous question looking at using capacitors to time the motion of a ball. So we've got the 120 microfarad capacitor in there, we've got a 9.6 volt EMF source, and we've got a distance of 0.12. Okay, so when the ball is touching the copper contacts, the capacitor charges because it's connected the circuit, and it's charged up to 9.6 volts. Once the ball has left the contacts, the capacitor discharges through a 1.3 kilo ohm resistor. When the ball has travelled a distance of 0.12 meters, it breaks the aluminium foil, so the capacitor stops discharging. All right, seems fairly straightforward. Let's move on to the next question. So we've got a graph showing how the potential difference changes according to a data logger. So you can see here that currently the ball is just sitting at the start. It's not moved yet because we've got it still at the 9.6 potential difference. It's here that it's going to be released, and this is where it breaks the aluminium foil to break the circuit. So this is the discharge time here, and that's what it tells you in the question. It says it's struck at T1. Okay, so it wants us to calculate the charge that passes through the resistor as the capacitance discharges. So first of all, let's see. The potential difference initially is 9.6 volts. So the charge initially is going to be the capacitance times that. So it's going to be 120 times 10 to the minus 6 times by 9.6. Let me grab my calculator. Let's work that out. So 120 times 10 to the minus 6 times by 9.6 gives you 1.152 times 10 to the minus 3 coulombs. So that's how much charge there is initially. We can see that it discharges to, what's that going to be? That's 5.5, I think. Yeah, 5.5. So the final charge is going to be C times the final potential difference. So again, 120 times by 10 to the minus 6 times by 5.5, and that gives us a value of 6.6 times 10 to the minus 4 coulombs. So the charge that's passed through must be the difference between those. 5.2 times 10 to the minus 3 minus the answer, giving you a value of 4.9 times 10 to the minus 4. I think this stylus is on its last legs, to be honest, but we'll have to proceed nonetheless. So that's 4.9 there. So final answer by finding the difference between those two values we've got. Those of you who were more eagle-eyed will spot we could have actually taken a shortcut because they both got the same capacitance, so we could just find the difference between these two and multiply by that. That would be fine, but that's fine for now. The next question wants us to find the maximum current. So that would be when we have maximum potential difference, because the two are directly proportional. So to get the current, we need the maximum potential difference divided by the resistance. So that was 9.6 was the max potential difference, divided by, it was 1.3 kilo ohms. So let's calculate that one now. So 9.6 divided by 1300 gives you 7.4 times 10 to the minus 3. So ten to the minus 3 amps, because it's current. Okay, so that's that one. So let's continue with this question. So we want the change in energy stored in the capacitor. So that's going to be half C V1 squared minus V2 squared. So that's going to be 60 times 10 to the minus 6, because it's half times C, times by 9.6 squared minus 5.5 squared. So let's calculate that now. So 9.6 squared minus 5.5 squared times 60 divided by 1 million, effectively giving you 3.7 times 10 to the minus 3. Ugh, horrendous. Let's try that again. Times 10 to the minus 3 joules as your final answer to that question. Sketch a graph on the axes of figure 3 that shows the variation of the magnitude of current in the resistor during the time intervals shown in figure 2. A scale is required on the current axis but not the time axis. So first of all, there is no current up until T1. So we can put that in straight away. So the next thing we need to do is figure out our scale. So our maximum current we worked out was 7.4. So let's go up in, I think the best we can go up on it is 4s on here. So let's do that. So the initial current was 7.4, which will be up here. I think I did that slightly too low, but you get the idea. Let's try and get that right. So it should be halfway up there. And then we can calculate the final current by doing 5.5 divided by 1300, which is 4.2, which will be around about here. And then once it's stopped discharging, obviously the current's going to be 0. So we get that section. So now we just need to get the shape right. So we know it's going to be like an exponential decrease for the current, because it is for the potential difference. So that's a bit too straight line for my liking. There we go. That seems about right, I think. So that's roughly what your graph should look like. Okay, so continue on to the next part. So they want us to calculate the time for which the capacitor is discharging. So we're going to use the potential difference at times t is equal to the initial potential difference, e to the minus t over rc. So what we're going to do is we're going to take v0 to the other side and take a logarithm. So we get this is going to be equal to minus t over rc. So we get t is going to be rc log, and we get rid of the minus sign by flipping around the v0 and the vt. So the resistance we know is 1300. We know the capacitance is 120 times 10 to the minus 6. And we need to times that by logarithm. Oh, blimey, that's horrendous. Logarithm of 9.6 over 5.5. And when we do that, we come out with an answer of 0.086 blah, 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 seconds. So velocity is obviously the displacement divided by the time. Well, its average velocity is, so we've got a displacement 0.12, and then we've got a time of 0.086, so the velocity is 1.4 meters per second, and that represents the average velocity over that time period. Okay, so then last part, discuss 2 reasons why your answer to question 1.6 is likely to be lower than the speed of the ball immediately after it struck. So what we've worked out in the previous part is actually the average velocity. So air resistance and friction are likely to act against it, so that's going to make essentially the time shorter, so that'll be one reason. And we need to think of another reason. I would suspect that we need it to break the foil at the other end. I doubt that's going to happen the immediate it's struck. You're probably going to stretch the foil a bit before you actually break it, so actually that's going to take time as well. All right, and that finishes question 1. Ooh, that was a long question. All right, let's move on to the next question. Okay, so we're looking at a mass spectrometer. So this is actually an application of both electric and magnetic fields, so it makes a nice question. So we've got a passage, so we've got a sample over here on the left, goes to an ionizer, which turns it into a positive ion, typically, gets accelerated in some sort of electric field, gets separated out by velocity, and then it's use a magnetic field to separate out by mass. Okay, so we've got a diagram showing the components in more detail. We've got positive ions created by the ionizer, as I said. We use an electric field to accelerate those ions. They emerge from the accelerator and go into your velocity selector, which is again another electric field. And then we separate them by mass in a magnetic field. Okay, so let's have a look at what it wants us to do. So explain what is meant by ionization first of all. So essentially is where that ionization is when an atom or molecule, I suppose, gains or loses electrons. All right, so fairly straightforward there. Let's see what one's next. Discuss the energy transfers that take place in the accelerator as the ion passes through it. Assume the ions are in a perfect vacuum. So if they're in a vacuum, there's not going to be any work done by any air resistance. But what we're going to do is transfer potential energy, electric potential energy, from the uniform field to kinetic energy of the ion, which is going to represent so we're going to decrease the electric potential energy of the electric field, and we're going to increase the kinetic energy of the ion. So let's get that down. All right, so that's what we've got there. So let's have a look at the next one. So figure 6 shows the path taken by an ion that moves through the velocity selector at velocity v. And then coming out the other side, we've got just one velocity. Discuss how the path changes when an ion enters the velocity selector with a velocity greater than v. So we've got a uniform electric field here, so the force on every ion is going to be the same. But they're going to experience different forces with the magnetic field, because if the faster you travel, the bigger magnetic force you'll experience. So the faster you travel, the magnetic field will essentially change the path of the particle, and then it won't go through the gap. So if the velocity is just right, the two forces will balance and it will go in a straight line. But if the velocity is too fast, the magnetic field will, or fast or too slow, the magnetic field will adjust its path so it can't go through the gap. All right, so let's put that down. Okay, so that's what we've got there, and like this is essentially the equation I was using to explain why the magnetic force changes there. Okay, so draw on figure 6, which I think was this one, the path of the ion that is suggested by your answer to 2 part 3. So we've got a magnetic field going into the page. We've got the positive ion traveling to the right, so using the left-hand law we can see that it's going to curve upwards. So let's sketch that on. So to start with, it's not going to do much, and then it's going to essentially curve upwards like this. Okay, so the next part says the ions created by the ionizer may have the same charge but a different number of nucleons. Discuss how the path of an ion in the mass separator is affected when it has more nucleons. So if they have the same charge and the same velocity, we're going to end up with the same magnetic force. But because the magnetic force is always perpendicular, it's going to force it into a circular path. So what we can do is we can equate those two equations. So we can equate the magnetic force with the equation of circular motion, which looks horrendous there. So we can cancel out one of the v's, and we can essentially change it to make r the subject. So let's do that. mv over bq. So the key thing here is b is the same throughout, so that stays the same. The charge is the same. The velocity is the same because we selected the right one. So essentially, if you increase the mass, you will increase the radius of the circular path. So let's get that down. All right, and that's what we've got there. So essentially mass and radius are directly proportional to each other. Okay, so some ions are created with the same mass but double the charge. The path of the ion shown in figure 5 is that of a singly charged ion. Compare with justification the path of a doubly charged ion through the mass spectrometer to a singly charged one. So basically what happens if we double the charge? So if we look at this equation up here that we had, if we have the same mass and we also have the same magnetic field strength, those are the same. So the only things that could affect the radius are the v and the q. So first off, we need to work out whether the charge is going to affect the velocity of your particle. So the particles are accelerated by an electric field. So if you put double the charge in an electric field, it should reach double the kinetic energy at the end, which means your velocity should be multiplied by √2. So let's have a look at that. All right, so that's what we've got there. So now let's look at it going through the velocity selector. So we've got double the charge and the velocity has been multiplied by √2, and then we're going to equate that to the electric force. So let's do that. Okay, so I had a look at the mark scheme for this question and it says something different. What it says is that velocity is independent of charge, so a larger mass, and so then if the velocity is the same, m is the same, b is the same, increased charge should decrease the radius. But I don't agree with that because it doesn't make sense, because it hasn't considered the fact that they have to go through an electric accelerating field before they reach the separator. So I disagree with the mark scheme on this question. I think it's a problem with these specimen papers. They haven't thought about it carefully, but this would be my answer to this question. All right, so let's move on to question 3. All right, so we've got an alpha particle with initial kinetic energy of 4.9 mega electron volts. It's directed towards the center of a gold nucleus. So we're looking at the closest distance to approach method by the looks of it. And it's got 79 protons in the nucleus. The alpha particle is brought to rest at S, a distance r from the center of the nucleus as shown. Calculate the electric potential energy in joules of the alpha particle at point S. So do we? No, we don't. We're just going to need to have it in terms of R. So any electric potential energy it has must have come from the kinetic energy of the alpha particle. So essentially, the electric potential energy is going to be equal to 4.9 MeV. But it wanted the answer in joules, so 4.9 times 1.6 times 10 to the minus 13, because it's mega electron volts. Oh, that looks like an 8. Minus 13. When we do that, let's get the calculation out. Here is 7.8 times 10 to the minus 13 joules. So 7.8 times 10 to the minus 13 joules there. Okay, so then it wants us to calculate the distance of closest approach. So from radial electric fields, we should know that the electric potential energy is Q over 4 pi E0 R squared. So the distance is going to be the square root of Q over 4 pi E0 times the E electric potential energy. So that's going to be 79 times 2 times the charge of an electron squared divided by 4 pi times E0, so 8.85 times 10 to the minus 12 times the electric potential energy which we've just calculated. So let's work that out. So I've got electric potential energy, so times by 8.85 times 10 to the minus 12 times 4 times pi. So 79 times 2 times 1.6 times 10 to the minus 19 squared, all divided by the answer, square root it, and we get a value of 4.6 times 10 to the minus 14 meters as an idea of our closest distance of approach. So we're approaching the femtometer scale with this one. Okay, determine the number of nucleons in the gold nucleus. So we've got the radius and we've got R0. So what you should know is that radius is equal to R0, a to the power of a third. So that means a is going to be R over R0 cubed. So we've got the radius, which is 7.16 times 10 to the minus 15, divided by R0, the radius of the hydrogen. In this case, it's going to use the minus this one. Cube that, and we end up with 197 nucleons there. Obviously, we have to have an integer number of nucleons. The target nucleus is changed to one that has fewer protons, and the alpha particle is given the same initial kinetic energy. Explain without further calculation any changes that occur to the distance r. So there's the same kinetic energy to start with. It has to reach the same electric potential energy. Now, if you decrease the charge, you're going to have to get closer to reach the same electric potential energy. So that means the closest distance approach is going to get smaller. Okay. All right, and that finishes question 3. Nice quick one there. So the first question wants us to define the gravitational potential at a point. So it's work done to move a unit mass from infinity to that point. So let's write that down. Not sure why we need all that space, but never mind. Explain why gravitational potential is always negative. Well, the first thing is that at infinity, the potential is 0. and gravity is always attractive, so the field must have done work to move the mass there. So the field must have lost energy for the object to gain it, if you like. So let's put that into words. Okay, so then, let's just group those. The next one wants us to calculate the gravitational potential at the Earth's surface due to the mass of the Earth. So if you look in your data formula booklet, you'll find the radius of the Earth, so we can calculate it very easily. So this is your equation. Got G. Oh, it's not behaving itself today. Let's try that again. Okay, so 6.67 times 10 to the minus 11. That's your G. If you look in your formula sheet, the mass of the Earth is 5.97 times 10 to the 24. And the radius of the Earth, or the distance between the where we're taking it and the center of mass, is 6.37 times 10 to the 6. If we do that, that comes out at minus 6.25 blah 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 times 10 to the 7. You can see that that's roughly 6.3 times 10 to the 7 joules per kilogram. Okay, so a satellite is launched into a geostationary orbit. Describe and explain two features of a geostationary orbit. So the orbit is above the equator, or in the plane of the equator, and it is always above the same location on the Earth, and it will also have the same time period as Earth, or the same angular speed as the rotation of the Earth. So let's put that down. Okay, so those are the two things that allow it to stay in a fixed location. The satellite has a mass of 1,200 kilograms, and the radius of its orbit is 4.23 times 10 to the 7. Calculate the gain in GPE of the satellite when it's placed into orbit from the Earth. So the work done is going to be the change in GP, so that's going to be GM 1 over final minus 1 over... Oh, blimey, what's wrong with this pen today? Sorry about this. This is atrocious. The initial distance. That's your general setup for this. So we've got a G of 6.67 times 10 to the minus 11. We've got the mass of the Earth, 5.97 times 10 to the 24. Got the mass of the object, 1,200. We need to multiply that by all of these values, so 4.23 times... Oh, what's wrong with this? 4.23 times 10 to the 7 minus... I can't even draw a line. Ah! One over the radius of the Earth. So let's calculate that, and when we do it, we get a value at the end of 6.4. No, we can give that to 3SF because we've got three significant figure values. So 3.38 times 10 to the 10. Why does my screen hate me today? Joules there. Okay, so that's how much work you'd have to do. Impulse engines are used to place the satellite into an orbit with a longer time period. Discuss any changes this makes to the orbital motion of the satellite. Okay, so if we equate our centripetal acceleration to our gravitational force, what you can see is that essentially the time period squared, oh god, is directly proportional to the radius of the orbit cubed, which is also known as one of Kepler's laws, Kepler's third law. The screen hates me today. So you can see that if you increase the time period, we're going to increase the orbit radius, and also increasing that would also have the effect of decreasing the velocity, because you can be traveling slower if you're further away. So let's put this into words. All right, so the question is, like, where has this second part come from? Well, it's essentially come from another equation like this. This time equating with the linear velocity in it instead of the time period. We can cancel out r and r squared, so we can see that if you increase r, we can decrease the velocity. That's where that second statement there comes from. Okay, so that finishes question 4. All right, so the last part of the longer answer question is looking at step-down transformer. So explain the purpose of the core in a transformer. So essentially it's there to make sure the magnetic field goes to the secondary coil. So it essentially guides the magnetic field from the primary coil to the secondary coil. Okay, so describe and explain 2 features of the core that improve the efficiency of the transformer. So first is we make it from soft iron, which reduces the amount of energy it takes to magnetize and demagnetize, also known as hysteresis loss. And we also laminate the structure to reduce the eddy current. So those are the 2 things we would change about the actual core. The other thing that you could change is the resistance of the windings, but that's not part of the core, so that wouldn't be an answer to this. So let's put that down. All right, so that's what we've got there. So the next one was just explain why transformers only work continuously when supplied with an alternating current. Well, this is all about induction, so we needed an alternating current, so we've got a continually changing magnetic field in the core. All right, so that's what we've got there. Let's flip over. So the primary coil of the transformer is connected to a 230 volt RMS AC supply. The current in the primary coil is 0.3 amps RMS. The secondary coil has 300 turns and provides an output of 20 RMS, so we've got a step down transformer, and a power of 65 watts. Calculate the number of turns on the primary coil. So what you should know is the turns ratio is equal to the voltage ratio. So you want to work out NP, so that's going to be the turns on the secondary, 300, times by the primary voltage, so 230, divided by the secondary voltage, so 20, and if we do that, we get 3450, so that's going to be 3.5 times 10 to the 3 turns. Calculate the efficiency of the core. So efficiency is power in over power out. We already know the power out is 65. The power in we can do by multiplying voltage by current. We're assuming that 65 watts is the average or RMS value for power, so 230 times 0.3, 65 divided by the answer gives you 0.94 or 94%. Did it give you an indication? No, so either of those should be fine. I always write the answer as both a decimal and a percentage, so then you never have to worry about what they were going for. Okay, so that completes section A of this paper. I do apologise again for the terrible handwriting at points. I'm afraid my screen and stylus are being very temperamental today, but this video is more designed to help you be able to answer the questions rather than you just be able to read what I've done. You can find that in the mark scheme if you want to pick up what some of these numbers were if you couldn't read them. So thanks for watching. If you have any questions or issues, please do comment and let me know. That I will be moving on and doing the section B a little bit later on.